Severo colloquium that is going to be given by Dr. Juan Cabrera, that we acknowledge already for accepting to be here. Dr. Cabrera defended his PhD thesis in 2008 at the Observatoire de Paris-Meudon in France, focused on the research for extrasolar planets with the transit method. After his thesis, he started a postdoc at the Institut for, I will say it in English, Institut for Planetology, in German I'm not able to do that, in Berlin, in Heike Rauer's group, continuing with publication of Corot results, but also analyzing NASA data from Kepler and TESS. Since November 2017, he's head of the Department of Extrasolar Planets and Atmospheres in the Institute in Berlin, where there are just over 20 postdocs and predocs dedicated to the search and characterization of extrasolar planets. He's author of more than 100 publications, with each about 26, and he has been member of the Scientific Council of the Space Mission Corot and coordinator of the Corot Exoplanet Detection Team. As you already know, Corot satellite was a pioneer in detecting transits from space and found the first terrestrial planet outside the solar system, Corot 7b. In fact, I don't know how to say. Do you say Corot in English or? Okay, I say it in French. Sorry, Corot. Nowadays, he's member of the CHEOPS science team and of the Plato performance team. As you know, Plato is an M3 mission of SS Cosmic Vision program, where his institute is leading the consortium of about 500 scientists from all the world, and engineers designing and building the mission's scientific instrumentation, and in which the IAA participates. The work he will present at this colloquium today, as you know, the title Extrasolar Planets, Recent Advances and Future Challenges, mainly related with the results they're dealing with in his department of extrasolar planets and atmospheres, and he will talk, of course, about planetary atmospheres, habitability, and biomarkers. Thank you very much for coming here, Juan.
So I'm going, happy to be here. I'm going to present the work that my department is doing on the characterization of atmospheres, and talk a little bit about chaos and play too. But one of the first things that I wanted to start with this result. I wanted to talk about water on the atmosphere of extrasolar planets. There have been several detections, and I think one of the most important recent results was done here in the Institute with this characterization of the hot Jupiter HD 209 and the detection of water in the atmosphere of this planet. This is a quite challenging measurement. I mean, the problem of characterizing extrasolar planet atmospheres is that planets are very faint. There is a very large contrast with the stellar light. And then you have to be very creative when trying to disentangle both signals. And this is one of the ways to do this. I will talk later about transit spectroscopy, but here what the idea is you can disentangle the signal from the planet from that of the star, taking the advantage that they move at different velocities. So at any time when you observe the spectra of the star, you also observe the spectra of the planet. And as the planet orbits the star, you can see the lines moving, even if you cannot see them individually, but there is a complex spectrum with lots of lines that you can follow this. And then you see a signal at the given orbital speed that you expect for your planet, and then you see the signature of this molecule. No? And this, okay, you have the experts here in the room, but I will not say more. But I think it's a very interesting result, and it's I mean, it was not clear 20 years ago that we would be able to do these measurements. Okay, so this is one of the results that I think are more interesting from extrasolar planets, is that it drives the way that we use our instruments. It drives the design of new instruments, because we try to detect things that are very, very challenging, but at the same time we learn about things that we didn't expect before. So this is what I will try to show. So, okay, this is HD 209. It's a hot Jupiter with a very short orbital period, and it was not unexpected to find water. What it was also more surprising, this was a result from last year. This is not work from our team. This is a different team, but they found water in the atmosphere of an extrasolar or super Earth, so a planet that was larger than Earth, but it's in the habitable zone of a star. Okay, and this is of course it's more difficult, because in principle those planets are smaller and it's more difficult to detect this signal. But it was very interesting, because it was the first time that we could find planets, this water, this molecule in one of these small planets. So here you have some information about the detection. You see that there are some uncertainties in the depth that translate into uncertainties into the radius ratio, and therefore uncertainties into the planetary properties. I will talk about this later. And this I have to talk now about this habitable zone. What does this mean? Well, because you know that we have been always looking for life. When people look for life, they think, okay, water is one precondition of life. So what does this mean when we are able to find this molecule? Is there liquid water on the surface of this planet? And this is the next question that we're going to have. And this is one of the examples for how do we interpret this spectra. You see that we don't have that many measurements. We have 2 transits from Kepler. We have 3 transits from Spitzer, also, that try to constrain but not too much. You can say you get the size of the planet, but you cannot say much of the atmosphere. And most of the information that we get on the atmosphere comes from these Hubble observations. But you see that it's not able to constrain between different models with different compositions, and I will show why later. Okay, of course, you talk about habitable zone, then you have to talk about life, but I don't want to talk about life. There are very nice reviews there. I think we could talk in the coffee break or later if you want during lunch. Same about biosignatures. Biosignatures that are molecules or processes that tell us that there could be life on the surface of a planet. Why are we doing this? I mean, this is one of the motivations of my institute. I mean, the goals of our institute is to find how planets form and evolve, find how how life developed on Earth, and if it's possible to find life in other planets in the solar system and everywhere. Okay, so this is what we try to do: study the origin and evolution of planetary systems, and for this we have to research into the interactions between the interior, the atmosphere, and all the processes that are there. We then search also for life and habitability, and which are the biosignatures that facilitate the detection of life. I mean, it's a criticized approach as well, and you can find many reasons here in this that we can also discuss during the break if you want. Because it's, some criticism is how can you look for life if you don't know what is life actually? You cannot put up a definition of life, okay? And the idea is the same. I mean, you don't try to search for what you don't know. And there's a sentence of Goethe, the German poet, that says, I mean, you can only find those things that you already know that they exist. I mean, so we look for things that we know that don't exist, and this is why it is important to find water. Water is, maybe we cannot say anything about life, but we could really say about, is there water in this planet, and what does this tell us about how this planet has formed? So just to define the basic notions of habitability, in principle, is that you can find an environment that can sustain life. And in this case, what people define the habitable zone as this region around a star where liquid water can exist on the surface of a planet, of a rocky planet. Okay? Why it has to be rocky, I will show later. And you have this idea. I mean, these 2 bodies are in the habitable zone of the sun, but only one is habitable, okay? Because the moon has no atmosphere, it cannot hold any liquid water. In the solar system, you have Venus, which also because of the constraints of pressure and temperature doesn't hold any liquid water, and Mars, this is the average atmospheric pressure and temperature. So, I mean, there are regions in the surface of Mars where you could find sometimes the conditions where liquid water could exist, but in principle, on average, it doesn't exist. So this is why when we find those planets, this is why it's important not only to characterize them from the period and mass, but also try to characterize those atmospheres to see if water is possible. One of the ways that we do this is with theoretical models of planetary interiors. This is the theoretical model of in the interior of a giant planet. It's 300 Earth masses, mostly made of hydrogen. And you see that at any point in time, you can find a region of the, or an area of this planet where the temperature is 300 Kelvin and the pressure is 1 bar. Okay, so you can find regions where you could have liquid water. But there is no surface here. So you will have liquid water, you have drops that will condensate, and it will rain, or it will fall, or something will happen with them, but it will not be an ocean. Okay? So we know that this exists in giant planets. The question is which is the same for super Earth. And this is the pressure temperature diagram for this particular planet, K218b. And you see again, this is one of the models I'll tell you which is the pressure temperature diagram. So here is the planetary surface in this direction, and below. And you see, okay, there is a region on the parameter space where there could be liquid water, but there is no surface to hold this water. The surface is much deeper if there is anything that we can call surface of this planet. I will show later why. So there will be rain again, there will be water or water droplets, but there will not be ocean. So this planet, although it's in the habitable zone, it's not what we qualify as an habitable planet. Okay, so this is a very different planet than what we find in the solar system, and we want to know why. Okay, why those planets are not existing in our neighborhood, and how do they form? Because the conditions of this planet are really different from Venus, Mars, or Earth. So what planets exist? To first order, the only information that we have is on the bulk properties, the mass and radius, and the orbital properties, the radius and density. No? And you see this is the diagram of what we know today. So you see the mass on the horizontal axis, the radius in the vertical, and you see here is the solar system. Okay, and here everything works fine. So everything goes along one line. So you can see the relationship between the density of those bodies, where do they form, how do they relate to the nebula, where they started. So this is great for planet formation theories. But when you start to put extrasolar planets, you see that there is a very huge diversity. Okay? Part of this diversity is related to observational biases and uncertainties, but another part of the diversity is real. Okay? One of the things that is real, I mean, we know that there are more planets with masses less than Neptune than above Neptune. Okay? We still don't know why very well, but it's surprising that most of the planets that exist are here, that we know that exist are here, although there is none in the solar system. Okay, this, of course, makes it great fun for the planet formation theories, but doesn't make it too easy to understand. This is one of the best knowledge that we have nowadays about the mass and radius of those planets, and it shows only those that have little uncertainty in the mass and in the radius. Okay, 25% in the mass is already quite good, and 8 in the radius. I will show later, Plato, we want to go to 3% on the radius and 10% on the mass. So really and second thing that you cannot see in this diagram, and most of those planets are with short orbital periods, too few days. The idea with Plato is to take this out to outer regions of the parameter space. Okay, why? Because here you see all small planets that we have here tend to be, here you see in this maze radius diagram, you can put lines of constant composition. It's a first idea of how do planets, what do they have in the interior. These planets, for example, along this line are dominated by silicates, so which is a good representation of what you have on Venus and Earth. Those planets will be complete line of iron, which is not realistic, but it could be more representative of planets like Mercury, which have a very dense core. And planets that, on the other hand, will have quite a lot of ice, which could be really representative for what we have in the outer solar system, in the Galilean moons, for example. Okay, so what kind of planets exist? You see that there are lots of small planets, and they tend to be rocky. Okay, but this could be an observational bias. Why? Because those planets have short orbital periods, so it's likely that all these atmospheres has been eroded. So only the rocky core remains. But we don't know at longer orbital periods if planets could exist with a significant amount of hydrogen in the atmosphere. Okay, primary atmospheres that still survive. According to theoretical models, this is possible, but we have not discovered them yet. Another difference, here you have Uranus-Neptune in the solar system, and here you have all this diversity of planets that start to be not only silicates, although you have here some rocky planets with masses up to 25 Earth masses, which is also something surprising. From the theoretical models, we expect after 5 to 10 Earth masses, those planets should have acquired a lot of hydrogen from the planetary nebula quite fast, and then become planets like those ice giants. This is not the case for these planets, and we still don't know why. And we don't know which is the largest rocky planet that we can have. I mean, so far we think that we are close to the record here. And when we go to, I will show later, we have found planets that, according to a theoretical model, they should have up to several hundred of Earth masses of rocky material in their interior. And we don't know how this 100 Earth masses of rocky material can reach there. You see another possible observational bias. This is transit time invariation and radial velocity. Transit time invariations is an independent way to obtain masses of planetary systems, but they tend to be lighter than the planets that we find with radial velocity. So this could be that we are still not 100% certain how to do transit time invariations. And this is why we prefer, in principle, radial velocity as an independent confirmation method, and also have all those efforts done here. So you see all this diversity, I think, but I prefer to see it in this diagram. This is what we put in 2014 for Plato. When we show, instead of the mass radius, we show the density radius, okay? And why do we like this? Here you see the same idea. You see the lines of constant composition, you see the position of the solar system planets, and all the planets that were existing at that time. So what we believe is, in the core accretion model at least, I mean, we start with little pebbles that merge together and then start to make larger bodies, which are principally made of silicates or ices. At some point, the core is so large that it starts attracting a lot of hydrogen, as I mentioned. So you get which is the maximum bare core that you can have in your system, and you start accreting gas quite fast. And then at some point, you will become a giant planet like those regular. So all the diversity that you see here, it's related to the sources of energy. You have, for those short period planets, you have additional sources of energy that inflate them. But there are all, as I said, I mean, here we have the largest cores that we can achieve, that they moved from 15 to 25 now in the last 5 years. And here you also find those very dense planets that we don't know how did they form at all. And maybe it's because they don't form the same way. Maybe those planets do not form by the core accretion, they form more like binary stars. And this is something that we want to check. Of course, the idea is to check this for different orbital periods around different stars of different metallicity, so we can try to learn something about the origins of those systems. And also, as I said, I mean, when we look to this diagram nowadays, this is how it looked like in comparison to 5 years ago. This is K218, just for example. And here, for example, we expect to find secondary atmospheres for those terrestrial planets, but we don't find any of those primary atmospheres. We expect to find them in the future at longer orbital periods. But for this, we need new tools, we need new measurements for achieving this. I was talking about the degeneracies. I mean, you have seen here that given a planet, it's very difficult to constrain which is the amount of silicates or water or ices that it has on its interior. No? So there are in principle 3 main components of planets that we believe. So we can put rocks, which are with iron silicates, dense elements. We can have ice of water, methane, and other compounds. And then we have gas, hydrogen and helium. And depending on how much you put of these elements, you can have different planetary interiors, which is quite degenerate. I mean, given a certain mass and a certain radius, it's not easy to see which is the right combination of all those elements that give you this planet. But what is important for us is that, of course, we expect some processes to dominate the formation of those planets. For example, if we have outgassing, we expect those rocky planets with some atmospheres, which could be rich in hydrogen or rich in water, depending also which is the redox state of the mantle. Okay, depending on which is this redox state, we will try to outgas more hydrogen or more CO2. And so if you have sublimation during formation, or you have been formed more outwards beyond the iceland, you might be more rich on water. And if you really manage to keep your primary atmosphere, then you will be dominated by hydrogen. This, of course, makes it very interesting, but also very difficult to characterize. Because also one of the reason is when you look at the planet and you only have its mass and this radius, how do you know what it's made of? I mean, this is an example. When you have an atmosphere which is dominated by CO2 or which is dominated by hydrogen, here you have the surface pressure and the contribution of the atmosphere to the radius of the planet, and you see that if your atmosphere is very light, the contribution to the radius will be very large. So you will find more of those puffy planets that would be comparable, for example, with Titan on the solar system, and that we could have very interesting regarding the atmosphere, a very extended atmosphere that has a significant contribution to the radius of the planet. And we have not found any evidence of those planets, but we expect to find it in the future. So now what we are trying to put is all those tools that tell us, okay, given a mass and a radius, which are the first information from the planet, what can we say about the interior, what can we say about the atmosphere? Another degeneracy in planetary atmospheres comes from the fact that, mostly what we see in this transit spectroscopy or in emission comes from the scale height. And the scale height, it depends on the temperature of the planet. That we have. It depends on the orbital properties, of course, and on the star. And we have ranges from 100 to 2,000 with not too vast uncertainty, 10%. But we have also the mean molecular weight of the atmosphere. And this depends on the chemical composition. This is the only way that we have to get an idea of the chemical composition. But it can be anything from hydrogen or water, CO2, and whatever mixture of it. So when we go to those transmission or emission spectra, this is what you see. Here you have, this is a classical example of a handmade, it's not real. But you see two different atmospheres with very different composition. This is dominated by water with some CO2, and the mean molecular weight is 23. And here you have a different atmosphere with nitrogen, some hydrogen and helium, and less water, 10 times less water. But still the mean molecular weight is the same. So the scale height will tell you, this is basically the same atmosphere. Try to distinguish between these two. There are ways. You have a different Rayleigh slope, but those measurements are difficult to get, and of course, even if you have some molecules that you don't see because they don't have any signature in your atmosphere, you have to infer them somehow, and then you are dominated by water and CO2. This is why we also look for water and CO2, because these are the easiest to find. So how do we deal with this atmosphere? This is one result. When we look at this atmosphere of K2-18b, we said we have found water, but we don't know how much water is in those planets. When you do the retrieval, any composition between less than 1 per 1,000 or up to 10% of water is compatible with those observations. And it's a very different when you look, for example, when you try to learn something about the nebula, where it formed. It's either there is, you have to explain how a planet can get enriched in so much water. Part of this degeneracy, of course, is that nowadays, at least for K2-18b, the measurements are dominated by the information that we have in these wavelengths, which is a very narrow range. In the future, we expect to, with Ariel or JWST, we expect to expand this range of measurements to a much broader range and try to learn more about those atmospheres. But for the moment, we are there. A second degeneracy that comes into those systems, in the scale height also you have the log G, the surface gravity, and this depends on the orbital parameters. This is the evolution of the stellar parameters and consequently which are the planetary parameters for this K2-18b. And you see that it has changed quite a lot. And those statistical uncertainties that you have, they do not represent the real uncertainty that you have on the properties. It's not easy to, this is an M-dwarf. M-dwarfs are particularly challenging, but one of the problems that is that the distance was not very well constrained, and with the Gaia release, second Gaia release, it was a bit farther away than what was thought in the beginning. So you see that in a few years, the planet went from a density of 3.3 to 2.4 grams per cubic centimeter, which makes, of course, a very different kind of atmosphere, a very different kind of planet. And so there are two ways to address this. I mean, first we try to get a best grip on the planetary radius. This is what we try to do with Cheops, because we also want to secure the ephemeris. This is another. I mean, the initial ephemeris were this from the observation of Kepler, and they were way off. Because of the uncertainties, we could not have been able to observe this with JWST. The period would have been lost by that time. So thanks to the reobservation with Spitzer, it was possible to secure the ephemeris for the next decade. Okay, so for some of those planets that we have found with Kepler or with K2, we will need Cheops, okay, to check reobserve those planets and tell us the ephemeris. And the goal of Plato is different. The plan of Plato is to characterize those stars to a very high degree of accuracy, so we can really constrain the planetary parameters. This is the position of K2-18b in this diagram of all known planets. Here you see again different lines of composition, and you see that because of those uncertainties, I mean, a single planet can is compatible with very different internal composition. Okay, so how do we try to deal with these uncertainties? Now, one of the ways that we have been developing in our department is so we have a good collaboration with people developing planetary interior models for solar system. So we try to adapt those models to the observation of extrasolar planets. And they built a model where they consider different layers for explaining a planet, where you put the iron-rich core, you put a silicate mantle, and then some envelope of ice and atmosphere. Then you mix all together, and then you see, okay, which kind of planets can I make with this, according to these theoretical models. This is not including any physics on how do planets form yet. Okay, this will be the next step. What is telling you this model nowadays is, I mean, if you have a planet with the mass of the Earth and the radius of the Earth, which kind of internal composition is compatible with this planet? And it tells you it's very difficult to make a planet like the Earth if you don't have a core that is at least 40% of the radius. Okay. And then on top of this core, you can put some hydrogen envelope, but it cannot be more than 30% of this planet at all. Okay. We still don't know which planets form. In case the Earth is actually with these two lines. Like the Earth has a lot of core, a lot of mantle, and basically no atmosphere. Okay, so you see that there is more on this, but at least it's telling us, okay, what can we say about those planets, which are the minimum information that we can get on the interior of those planets, and then can we relate those properties of big cores or no core at all, or big envelopes, to the way in which they form. Of course, the model has lots of degeneracies, okay, so we cannot constrain very well which is the size of the core unless we add new observables. One of the new observables that we could add is the K2 love number. This is the fluid K2 love number. And you see here in this diagram, what you see is you try to retrieve which is the size of the core with the size of your mantle on this synthetic population. You see that there are lots of, the core is okay, but there are lots of degeneracies between the mantle and the ice and the gas layer. If you are able to say something about the internal distribution of the planet from the K2 number, then you are able to constrain much better the properties of this planet. We are unfortunately far away from measuring K2 for those planets. We have made progress recently with very accurate photometry on hot Jupiters. And these are some simulated results of one PhD student of our group that try to say, okay, assume that I have a real planet with a given K2 value, which is representative for what we expect for Jupiter-like planets. Can we retrieve this from the photometry, depending on the different instrument that we have? So we started with TESS or Cheops, and they say, okay, it's not enough, it's not good enough. You go to Kepler, Plato, and JWST, and then still, okay, when you go to JWST, you start to be able to say something about the interior of this planet. Okay, so we expect to do this in the future with giant planets. With rocky planets, it's still far away. Also for rocky planets, you have to be careful about the assumptions. I mean, this K2 love number works very well as long as the planet is in hydrostatic equilibrium, which is not true for every planet, like Mars. But it's a way, let's say, add new observables to say something about the planet. About the generalities in planetary atmospheres, also to show what is the difficulty that we have in retrieving the data. When you see the structure of your atmosphere, again, the pressure temperature diagram, you have here different lines depending on which is the orbital distance. So we are here talking about very hot Jupiters. And this is the region of the parameter space that we cover with transit spectroscopy. So you see here this, actually putting an isothermal atmosphere is not such a bad approximation, but the disadvantage is that you cannot say much about what is going on in the interior of the planet, okay, when you just probe this region. And there is another very interesting result from here, that they observed Jupiter like if it was an extrasolar planet. And this is what you see. I mean, you see hazes, you see ices of water, but then you cannot say much more about the atmosphere of Jupiter just with transmission spectroscopy. Okay? So if we want to observe or characterize in depth planetary atmospheres, we cannot go just to transmission. We also have to try to observe emission. Okay, in emission you typically go deeper into the atmosphere, but then you have you reach you can say more about the composition about the adiabatic region, but then you have to bring it to the model more complexity. Okay, you have to be able to describe somehow your transport, you have to be able to describe your chemistry, you have to be able to do more things. And the main limitation, as I said, this is also a very nice result. I mean, nowadays the information that we have on the spectra is very scarce. We have WHST here on around 1 micron, and then we have Spitzer, and that's it. Okay, and you see that the model is very much constrained by what happens here, where we have good data, but we cannot say much about what's going on at longer wavelengths. No? We hope that this will change with Ariel and JWST in the future, where we have access to much larger wavelength range. Another region of the parameter space that had been sampled, and I think Antonio García Muñoz was giving a talk some weeks ago, and he talked about these escape processes and all what happens here in this upper part of the atmosphere, where also the photochemistry dominates. Why is important also photochemistry? Because it can change the way in which your molecules react. Okay, this was one study that Lee Grenfell from our group did 2 years ago, where it was a discussion in the literature about planets of super-Earth, of those super-Earth atmospheres, which had lots of water in the atmosphere, okay, really large amounts. And he started to think, okay, but wait, if we have lots of water and then in these very highly radiated atmospheres, this water will photodissociate. Okay, so the water will become hydrogen and oxygen. There are ways in which oxygen reacting with other molecules that are also plausible in the atmosphere, like CO2, will form oxygen. And actually what you have is hydrogen and oxygen, which is not a very good idea in your atmosphere because this is very reactive, and then it will produce lots of water in liquid state that will rain down into the surface of the planet. Okay, so it's one way to get liquid water on the surface of the planet coming from the atmosphere. And also it puts a limit of which kind of compositions are possible for those super-Earths. Okay, so some of the values given in the literature are not compatible with these photochemistry constraints. Okay, because there are some regions of the parameter space on this pressure temperature that are really explosive, where those hydrogen and oxygen will recombine in an explosive way, depending on which is the concentration, of course, of the other major molecules in the atmosphere. So this, as you see, it starts to get very complex, and this is the model that we are using in our department. So we have a 1D model coupling the climate and the chemistry. So for the climate, you have to put different assumptions about the radiative transport and all the, all the constraints, the boundaries that you have on the humidity, on the water concentration of your atmosphere, and then when you reach an equilibrium, you check also that the chemistry is consistent with the physical properties that you find in your atmosphere, and then you have to talk about photolysis, reaction rates, and all these different there are also quite a lot of uncertainties on those reactions and different processes. There are also loss processes that can remove some of those molecules from your atmosphere, and production. And then you try to find, you iterate all these models together until you reach an equilibrium, and try to define your atmosphere. And this model was developed for the study of atmospheres like the Earth, trying to, and then putting this Earth around different type of stars and see if we could be able to understand the chemistry and the physics of those atmospheres and see if we could be able to retrieve, for example, those biosignatures in case they exist. Well, what you see is that the atmospheres change a lot. If you take the atmosphere like it is on the Earth today and you put it around an M dwarf, in black you have the current structure of the Earth's atmosphere with this ozone here absorbing a lot of energy and heating the atmosphere. And when you put this around an M dwarf, because of the spectral energy distribution of M dwarfs is very different, you find a different photochemistry, and all this ozone is lost in your atmosphere. For the same amount of oxygen, you will not see ozone in the atmosphere, in the upper layers of the atmosphere of this planet. Okay, and also with the interesting of this study, also from Marcus, a PhD in our group, is that he studied the different elements stars are active. So depending on the activity level of the star, you will also see changes in the atmosphere, and you can translate all this photochemistry and all these changes into the spectrum that you will retrieve, and see which are the dominant molecules in those planetary atmospheres. Okay, and what we try to do next is the detectability of those features in the atmosphere. And here you see it's a bit hopeless because the changes in the depth is about 2 ppm, which is not something that we can achieve now or in the near future. But at least, okay, tell us two things: that it's going to be difficult to measure those molecules in the atmosphere of extrasolar planets, but that we at least have the tools to study this and to make predictions. Because for example, in this case, what's interesting to see how flares were weaken the role of methane in the heating of the middle atmosphere, and this changes when you change the temperature, you also change the chemistry of your molecules and your reactions. And also shows where do we have to do more theoretical work. The idea is that it's very important to have all this theoretical understanding of the physical processes in atmospheres to be able to understand the observation that we get. Another link that we are trying to do in our institute is, okay, we know that the interior of the planets will also have a very important role in what happens in the atmosphere and how the planets cool. Okay, we will see. This is running out of time, sorry, but this is an interesting study that was done also from a guy in our group. Is that we are studying also planets around M dwarfs. M dwarfs in the beginning of their life, they are much brighter. Okay, so when you look at the habitable zone, the region around which you could have liquid water, in the beginning of the age of the system, you have to be much farther away. Otherwise, your water will boil in the atmosphere. Okay, so this is the evolution of the habitable zone in time for those M dwarfs for different assumptions on the planetary atmosphere. And here you see the planets of TRAPPIST. Okay, so it's true that these TRAPPIST planets are now in the habitable zone of the M dwarf, but they were not always so. If we assume that they were not migrating in the past, past million years, at this point they were not in the habitable zone. So the water in this atmosphere has evaporated. Photolysis, as we have seen, conducts to water losses, and you lose the hydrogen in your atmosphere, so maybe they don't have any water at all. Okay, what comes here in your rescue is that this can be the case, but still, if there is any water in the interior of your planet, this water will outgas. Okay, and later on you can develop again, after some billion years have gone, and some water on the surface of your planet. Okay, and then your planet is habitable again. This is a promising result from M dwarfs, because otherwise there will not be many M dwarfs that are habitable. But it also is something that we try to take to understanding the evolution of the atmosphere of the Earth. The atmosphere of the Earth has changed a lot during history. And even if there was during a long period of time life on Earth, we were not always able to detect that life, those signatures of this life. And so one of the things that we want to do, we expect to observe planets at different stages of their evolution in the future with Plato. So we want to see if we are able to understand how to describe those atmospheres, and also which is the influence of those atmospheres in the thermal history of the planet. This is one model that considered the Earth during the magma-ocean phase at the very earliest stage of the evolution, when the planet was very hot, and there was magma liquid magma on the surface. And on top of this magma ocean, there was an atmosphere with a lot of water. And this water it's a blanket for the atmosphere because it only lets you irradiate in certain wavelengths. And therefore, it controls which is the thermal history of your interior as well. Depending on how much water you have, how much atmosphere, you can have different cooling times and also different spectra. Okay, the spectra evolves a lot as long when the surface temperature changes. And the advantage of this model is that we can consistently study which is what's happening on the magma ocean, which is the outgassing that we have, and which is the effect on the atmosphere on those planets. So I think I ran out of time, but at least I wanted to show this. I mean, this is what we want to do. I mean, in the short term, we have Cheops flying. That it's doing now the commissioning. It's in orbit and everything is going fine, but I'm not allowed to show any plots because the PI has asked everybody to wait until they prepare the press releases, but I can say that it's working fine so far. Cheops is a small mission. It's 30 centimeter satellite and in white light, and the idea is that it will precisely characterize some of those planets that we know exist, but we don't have enough good radios. And the idea is to get this good radio so we can say something about the internal structure of those planets and how did they form. The next step is Plato. Plato will be launched in 2026. And 2026 is more ambitious because we want to discover new planets up to the habitable zone of the stars like the Sun, so planets like the Earth with one Earth radius, one Earth masses, with very precise mass radius and ages. I mean, for all field stars, it's very difficult to get ages. And the only way that we have this in an independent way is with astroseismology, so there is a lot of interest also in the astroseismology results. Plato has these both goals, to discover planets and to characterize the stars precisely, to learn also about the interior, well, all the stellar processes that are important for their evolution. And in the future, later on, JWST and Ariel will observe the atmosphere of those giant planets to see what can we say about also those formations with those chemical compositions. And in the far future, what we are now proposing for Voyage 2050 is contributions to different missions. Well, LIFE is an European one, interferometry from space, building on Darwin, to characterize the atmospheres by direct imaging. As you said, it's very challenging to do this on transit or emission, because for transit you have few of them per year, you have longer orbital periods, and also you cannot probe the whole atmosphere with direct imaging, with emitted light, reflected light. And also you are able to separate well, you can get direct photons from your atmosphere. It's easier to integrate more signal. So this is being proposed now for ESA. Other contributions are HABEX and Dubois, are American-led observatories, where Europe could have an instrument contribution, like a little bit like JWST. Okay, so I think I ran out of time. Thank you very much for your attention. If I can take any questions.
Two ways of discovering new planets, which is by the rate of velocity, temporary varying rate of velocity, and transits, when the planet passes over the star. Are there many planets discovered by the light they reflect from the star? I mean, the albedo.
For lots of known planets detected by transit or detected by radial velocity. Now, there are people who claim that they have discovered planets just by reflected light, but they could not be confirmed independently. Okay, so far we have reflected light from extrasolar planets, And we use this to characterize the atmosphere of those planets. It's interesting, but we don't have detections, to my knowledge, just from reflected light. Because from emission is another question. From emission, we have lots of these direct imaging planets. And more will come in the future, but they are still quite hot, and it's emission what we see, not reflected light.
Okay, my second question is, I think it's not working.
No, it's for the streaming, but we should check if it is on. But it's not for us.
No, it's not working. Anyway, my second question is finding planets in open clusters, for example.
Úsalo es para el streaming. It's for the streaming.
I'm sorry. Finding planets in open stellar cluster, for example. They give us with very good accuracy the age of its members. Let's say question 2A. Are there many planets discovered in open clusters?
Discovering clusters, but they are not very well characterized. One of the problems that clusters have is the stars are all together, as seen from Earth, and with the pixel scales that we have in the instruments that we use, it's not easy to disentangle different stars in the cluster. In the star. The pixel scale of Plato is 15 arc seconds. Okay, so it's, you will see the star blended, and you will not be able to say which star produces the transit. And say for radial velocity, they also have difficulties to extract the information from one single star. And okay, also depending on the cluster, there are not so many stars, so the statistics are not very good.
Okay, so let's take us to question 2B, which is in case we find some planets in orbit of stars in stellar clusters, open stellar cluster that we know the age very well. What would bring us, knowing very well the age of the parent star, what kind of knowledge would add to the planet, to our present knowledge of the planet? Because you mentioned how a planet evolves. Open clusters don't last much. They last, let's say, millions of years, or tens of millions of years. So in case we find planets in these places, there will be young planets. But with the age very well determined, at least the age of the parent star. In this case, what will this tell us about the planet? How would this increase the parameters of the planet?
Slide I could not show it, but shows how planets evolve in time. For giant planets, it's boring because they just cool and differentiate, and that's it. So you will see how the radius shrinks with time, and you will be able to, when you look at those clusters, you will say how fast do those planets shrink, okay, and say something about the energy distribution in the interior of those planets and internal state. For terrestrial planets, it's more interesting because we have shown that they go through different phases depending on age. Okay, so there is this loss of primary atmosphere, and those loss processes are very interesting, and we are trying to characterize them. It's very difficult to characterize it precisely. There is this time of cooling and differentiation that, of course, is very interesting also to see how does this compare to the solar system, and they go also through these magma ocean phases that are also interesting to observe. They may or may not develop plate tectonics, and then they tell you also something about which is the thermal structure of those planets, which is the cooling processes, which is how this is related to the properties of the mantle. It's not clear that we can detect plate tectonics for extrasolar planets, but there are people trying. They develop secondary atmospheres that we also want to characterize, and there are all those outgassing processes that we want to understand and see how they relate with the composition of the mantle. And then, of course, they can develop tertiary atmospheres. So all these things we can tell about the ages of those systems.
Yes, but it seems that maybe I'm wrong, but it seems that these processes, they take longer than the age of an open cluster, which have a few tens of millions of years. How long does it take, this process? It's longer, isn't it?
Not the expert to compare all these things. I know that if you look at the distribution of ages of clusters, there are gaps we have very young clusters that are very well characterized, and then we have field stars which are very old, and in between we don't have many statistics. Okay, so it's true that what we observe clusters will not be representative from the full history of planets. This is why we want to go further and try to get the ages from those field stars, and then we can see those planets at different ages and get more statistics.
Okay, here.
All right. Thank you very much, Juan, for that very nice talk. Actually, you cover many aspects and was really a little bit difficult to digest all the information you're giving up. I have a comment and a question. The first comment, I fully agree with you about the degeneracy in the atmosphere. Emission, they actually provide much more information than transmission. That is definitely no doubt. That's why I would expect that James Webb will provide much more information about the atmosphere. And I have one question which wasn't clear for me about the breaking the degeneracy in the planetary formation. You talked about the radium, mass, and a new parameter called K2. Sorry, I missed that is what is K2 and what is actually being adding in for breaking the degeneracies.
For when referring to one or another, let me see if I can find the. In this case, what we are measuring is the moment of inertia of the planet. Okay. So this is telling us which is the internal distribution of matter. If it's very much compressed into the, concentrated into the core, or it's homogeneously distributed. It's not to measure, but okay.
Okay, thank you. Cool.
It's another idea coming from the binary star. The K2 number means the degree of concentration of mass from 0 to R. Okay, that's this information.
So in addition to the density, mass rate, you also give you an idea of the concentration.
Yes.
But K2 is
You need the orbit and to measure the different position of the orbit, the cross by the perihelion and so on, in order to.
So for you it's quite well known. Sorry. No, just only that. Yeah, for other people are really well known, but not for me. Sorry.
Question? Yes, Pedro?
Hi, Juan. Thanks for the talk. Since the discovery of Proxima B, there have been papers claiming in favor of or against the possibility of the habitability of Proxima B, the presence of an atmosphere or not, presence of water, many other issues. We know very little about all these exoplanets. We are starting to characterize in some way the atmospheres, but we are far away from understanding them properly. We don't know anything about magnetic fields around the planets that could protect them from the radiation from the star. But climate models, Earth climate models, recent analysis have brought back the possibility that Proxima B could be habitable depending on the amount of clouds that the planet has. You in your group are studying climate models with the composition of the atmospheres. How all these mixed up to make a planet like Proxima B habitable or not? Thanks.
A good question and very difficult to answer because of all those processes that happen on the atmosphere. I mean, with Proxima B, we have an additional limitation that we only know the mass, or minimum mass. We don't know the radius, so we can say little about what we expect in the atmosphere. Okay, and also it's our model is 1D, which is makes a lot of sense when you try to describe planets like the Earth around the sun. But when you go to M dwarfs, you expect that down for the same insolation as the Earth receives from the sun, they will be tidally locked. And at this point, you start to need 3D models because the atmosphere then behaves in a completely different way. So the model that we have, well, this could be good news or bad news depending on who you ask. I mean, some people think that actually the habitable zone is extended to hotter atmospheres when you have this tidal locking, because you can redistribute efficiently your heat in the atmosphere and you can have clouds that reflect those light and then have better conditions. But we don't have this in our group. So this is something that it's open. But again, I mean, the second issue is, I mean, for me, the most important is the bulk properties, because here you have K218. I mean, in theory, it's in the habitable zone, but we know that, okay, anyway, we have no chance to find liquid water on the surface.
If there's no any question more, then thanks again for coming here for such a nice talk. Thank you.